we think with the right hardware, optimizations, 90% sparse should give you more than a 10x gain. So we're not talking about 50%, 20%, 30%, but we're talking about orders of magnitude here.
All right, everyone. I am here with Subutai Ahmad. Subutai is VP of Research at Numenta. Subutai, welcome to the TWiML AI podcast.
Thank you so much for having me, Sam.
Let's get started like we do here on the show by having you share a little bit about your background and your journey into the world of AI.
Sure. So I've actually been in deep learning and something called computational neuroscience since the late 80s, long before it was called deep learning. And I did research in understanding models of the brain and how that impacts machine learning in the late 80s and early 90s. I couldn't really see how to do anything practical with that at that time. And so I sort of switched gears and did research in more traditional machine learning and then did a couple of startups. About 17 years ago, I ran into Jeff Hawkins and Donna Dubinsky when they were founding Numenta. And it sort of all my worlds kind of came together at that point. Numenta
Nice.
as a company is really trying to show how we can take the neuroscience and really translate it eventually into practical systems. And so I've been at Numenta doing research for the last 17 years on that topic. Very fortunate to be able to do that.
Oh, that's fantastic. Yeah, we throw around this idea of deep learning being biologically inspired all the time, but I think Numenta is one of several places that's trying to push that idea of biological inspiration even further. Can you talk about the company and kind of the core ideas that you're researching?
Yeah, I think deep learning, has been somewhat biologically inspired, and they're definitely, the idea of modeling a neuron and some of the ideas behind convolutional networks and so on are directly taken from the neuroscience. But by and large, if you look at neuroscience, it's pretty far from a lot of the details. It's very, very abstracted out, and so the core idea behind Numenta is deep learning is great. It can really solve a lot of practical problems. But if we really want to understand intelligence and build truly intelligent systems, we need to go back and see what have neuroscientists learned and how can we, take those properties and create sort of algorithms, understand it from the algorithmic standpoint, and then incorporate those ideas into deep learning. We feel just, building bigger computers and faster computers and throwing more data at it is all great, but that's not going to lead us to intelligent systems. So we think it's we have an existence proof. There's an amazing thing, the brain, that is super intelligent. It's far more intelligent than any deep learning system out there. Why not try to understand what's going on there and see if we can apply that to practical systems?
When you think about some of those core things that neuroscientists have learned or that neuroscience teaches us that we can put to use in building learning systems, what are those things? What does that landscape look like?
Yeah, there's quite a lot. Neuroscience as a field has really exploded in the last 20 or 30 years. Many people may not realize this, but the experimental techniques have really gotten extremely sophisticated. Um, and there's many things in the neuroscience now that we can actually apply to practical systems. At the same time, there's a ton of detail in neuroscience that is not applicable to practical systems. So it's a bit of a challenge to figure out exactly where to draw that line. What aspects are really important and what aspects are just sort of more biological detail that don't impact practical systems. So kind of the some of the big items that hopefully we can get into more detail on, ideas like cortical column, the idea that there's a common microcircuit that's underlying all of intelligent function. The idea of the neuron itself, neurons in biological brains are much more sophisticated and powerful than the neurons we use in deep learning. Even core representational ideas like sparsity, the brain is extremely sparse and leads to a lot of efficiencies and other properties. Can we extract some of those ideas and incorporate it in? Even some ideas like the brain is inherently a sensory motor system. We're constantly moving around the world, and we learn by movement and we learn the structure of the world through movement, and this ties into how cortical columns are set up. So all of those ideas are somewhat different than what's in deep learning today, and those are concepts that we think there's a lot that's understood now, and it behooves us to kind of incorporate that into deep learning systems today.
So this idea of a cortical column as this fundamental microcircuit is a compelling one. It's not something that I've heard of previously. Can you dig into what that means, what this microcircuit looks like, and what we know about it?
Sure, it's actually a fantastic idea. It's an amazing idea, and this was, I think, first proposed by a neuroscientist called Vernon Mountcastle in the 70s. And what he noticed is that wherever you look in the neocortex, so first of all, the neocortex is kind of the largest structure in our brain. It's really where most of intelligent function actually happens. And whether it's visual processing, auditory processing, language, high level thought, that all occurs in the neocortex. So what he saw is that no matter where you look in the neocortex, you see a very, very similar microcircuit. Very similar connections between the layers and between neurons, similar neuron types, and a sort of a prototypical architecture. And our entire neocortex has somewhere around 150,000 cortical columns. So each cortical column is about the size of a grain of rice, and it's sort of sprinkled throughout our neocortex. And like I said, they all have this common architecture. And
And
sort of
when you
the
say that, when you say common architecture and connections, the picture that pops up in my mind is kind of the neuron and the dendrites and these connections, but it
yeah,
sounds like you're talking about a higher level structure. Is that right?
yeah. So the neocortex, the way it's structured is it's like a big flat 2D sheet that's sort of scrunched up and stuck into your brain. But if you were to flatten it out, it's about a couple of millimeters thick, and there's several layers, down that thickness in that dimension. And so there's about, neuroscientists say, roughly 6 layers, and these layers have a intricate connectivity between them. So there's different neuron types that are in different layers, and they connect in a recurrent circuit. And that architecture is what we mean when we say that's repeated throughout the neocortex. So it is a little bit complicated to go through, but there's, I would say, probably 50,000 or 100,000 neurons inside a cortical column, and at a fairly sort of prototypical connectivity structure between them.
And what have we learned about the columns themselves and their behavior? And I'm imagining this is something that might try to model computationally as well.
Yeah, yeah. There's a lot we can do computationally, and what neuroscientists have found, again, there's this common structure, and the proposal by Mountcastle is that the reason a visual area is a visual area is not because there's anything really fundamentally different. It's just that the inputs are different. The learning algorithms and the architecture is largely similar to the auditory cortex or to the language areas. And neuroscientists have even done this experiments where you sort of swap modalities, and you take an auditory cortex and you feed it visual information, and what you see is you actually see visual feature detectors show up in the auditory cortex. And so that tells you there's a very similar kind of algorithm. It's not about the sensory modality, it's about the common algorithm. So
Meaning that, just to interject there, meaning that we talk about the convolution being neurologically inspired. Is the suggestion that that's a software feature as opposed to a hardware feature,
exactly,
so to
yeah,
speak?
yeah, so to speak, yeah. So convolution sort of says basically that you have sort of similar feature detectors, throughout your visual field.
Mm-hmm.
So that's, and you do see that in the visual cortex. You see very similar features across. What this says is even more, it takes that sort of one notch up. It's like the entire architecture.
Mm-hmm.
It's not just one little feature. It's sort of the entire architecture is really preserved across sensory modalities, and this is
Mm-hmm.
an amazing thing. If this were true, and we believe this is largely true, is in order to really understand how to implement intelligent systems in a neocortical way, you sort of have to understand how one cortical column works and how
Mm-hmm.
multiple cortical columns interact. And then it's just essentially a scaling problem. You
Right.
just build more and more of them. So that really simplifies the process. And from a computer scientist point of view, that's great. It's like there's one thing we need to understand. It may be
Hmm.
complex, but it's not that complex. We can
Hmm.
understand it, and once we understand it, it's a scaling issue.
And so, how far along are we in this journey to understand the cortical column?
Yeah, I think we've made a lot of progress in understanding it. There's still a lot of work to do. One of the so if you look at convolutional neural networks, they mimic maybe one or two layers of this six-layer structure. So they mimic a small piece of that. Some of the things we've learned is that every cortical column is actually inherently a sensory motor system. And what I mean by that is every cortical column gets sensory inputs, and every cortical column actually sends out motor commands. So when you look at the visual area, it's not just a feed. It's not just an area which gets visual input. It actually sends out signals, to your eyes, for example, and your head to move your, head and eyes around. If you look at the so-called motor areas, they actually get sensory input as well. So there's no such thing as a sensory area or a motor area. Everything's an inherently sensory motor area. And what we know is that mammals in particular and humans, we really learn by moving around the world. So this algorithm is inherently one that's constantly driving action. It's constantly making predictions. We see when our predictions are correct and then when they're not correct, and we learn from those mistakes. And that's really how we learn about the world. We're not just passive systems that getting billions of images as input, and then suddenly we can recognize cats and dogs. We inherently understand the world and the structure of the world by moving around and making actions and stuff. So that's a really big component of it. Um, Another sort of really interesting thing is that if the cortical column is the same everywhere, the implication of that is that if some area of the brain is doing something, it must be doing that algorithm everywhere. So if you look at high level thought and what's required for high level thought, well, the same processes must be occurring also in low level visual areas and auditory areas. Um, and what our theory says is that every cortical column is actually its own independent modeling system. So every little cortical column is building a structured model of the world through movement by understanding how movement shapes perception and builds up a model of the world. And all of these cortical columns, the way they work is they interact and they with each other, and they come to a consensus about what is the current percept that's coming in. And through this sort of voting algorithm, uh, that's that's essentially what we are consciously aware of. Every we have thousands and thousands of these cortical columns, each working independently, and then they come to a consensus about what actually we are seeing and doing. So it's an extremely distributed system of lots of independent modeling systems. Again, this is very different from the way deep learning systems are structured today, right?
It raises a lot of
uh,
really interesting questions for me. Like,
yeah.
we talk about these a distributed system with lots of common components. One view is like a swarming kind of thing where
Mm-hmm.
everything's the same and you have these voting mechanisms. But you've also described in talking about the visual versus auditory function a degree of specialization. And I'm still trying to wrap my head around,
Yeah.
like, is that hardware or software specialization? Meaning, does the almost like kind of, is there like a bone marrow kind of, is a cortical column like a bone marrow and it like physically changes to specialize, or is it just changing thresholds or software things?
Yeah.
Do you
Yeah.
know
That's
the
a
answers to questions like these?
I mean, we know some of it.
Yeah.
It's a great question, and it's something that's puzzled neuroscientists for a long time. If you look at the auditory area, you see auditory neurons, and if you look at the visual
Hmm.
area, you see visual neurons. So what's common there?
Yeah.
Well, what's so it's similar to a deep learning system in the sense that you can take a convolutional network. If you feed it visual information, it's going to learn edges and corners and so on. If you feed it auditory information, it's going to learn auditory features. So
Hmm.
it's the same thing. There's a learning algorithm that's going on, And because the input is different, it's just going to learn different things. And you can't just look at the end of the day and just probe it and see what it's learned. You have to understand the learning process itself. So it is, the hardware is essentially very, very common, but the sort of emergent functionality is very different because the inputs it gets is very different throughout its life. Um, I mean, there are some differences between auditory areas and visual areas. So there's specialized color detectors and things like that in the visual areas that you don't see in the auditory areas. And so, but those are really in the details. If you step back and look at the large scale architecture, there's huge commonalities across them. So, yeah, it is interesting. It's fascinating to think through.
Yeah,
Yeah.
absolutely. So the cortical column is kind of this higher level architecture. You also mentioned the neuron itself and
Hmm.
the way we've been modeling that for deep learning versus the way we think about that from a neuroscience perspective. Can you elaborate a bit on that?
Yeah. So if you look at a deep learning system, the basic idea of what a neuron does is it takes a very simple function of the input and computes a very simple output. So it basically takes a linear weighted sum of its inputs and passes it through a nonlinearity like a sigmoid or a ReLU and then outputs something. It's a very
Mhm.
simple idea. That idea has been around for more than 100 years. It's called the point neuron model. And that basic idea in our mathematical system and practical system really hasn't changed. But if you look at the biology, real neurons are nothing like that. Real real neurons, you mentioned these dendrites. The
Mhm.
neurons have really complicated dendritic structures, and these dendritic structures is where neurons get input, and the neuron actually does very sophisticated processing of its input through these dendritic structures before actually computing an output. And so there are many, many layers of this, but um, a neuron is a pretty sophisticated computing device in the biological brains. And so, we've been sort of thinking, what aspects of that do we actually need to model in deep learning systems? Are there advantages to these dendritic structures? And when we think about things like continual learning, the fact that humans can constantly learn new things without forgetting stuff. Deep learning systems are not good at that, and we think the dendritic structure and the nonlinear processing that goes on in these dendrites and neurons is actually critical to how we learn new things without forgetting stuff. So that's an example of some functionality that's difficult today in deep learning that could be improved if we could incorporate some of these properties.
I'm curious what the neuroscience says around like the are these cortical columns and the neurons are they fundamental for memory as well as kind of the processing? Like, is it uniform across these very different modes as well? Some of the more recent deep learning research directions are like incorporating memory into deep learning systems as a way to get closer to the kind of intelligence that we exhibit. But I'm wondering if you're saying that, well, there's a single thing underneath from a biological perspective.
Yeah, I mean, it all has to be done by neurons, right? Somewhere, and
Right.
and yeah, exactly. It's nothing else. So it's in the brain, memory, learning, language, all of those functions. A large part of it happens in the neocortex, and a lot of it happens in what's called the hippocampus and hippocampal structures as well. And all of those, both of those structures have the exact same type of neurons that I was talking about, what's called pyramidal neurons. So they have the same complicated, nonlinear integration. So those properties of neurons are common for all function, all intelligent function, memory, language, speech. As you and I are talking and listening to each other, that's what we're doing. Our dendrites are processing away and creating these representations.
To what degree are the notions around like spiking something that you're focused on in your research?
Yeah, so neurons send signals to each other by initiating a spike. So it's an electrical signal that goes from one end to the other. We think we're not sure that that's really critical to model or not. We do need to communicate from one neuron to another, but it may be okay to just put a number in a memory location. That's what happens in deep learning, and that may be just fine. It is true that spiking is primarily binary. Like a neuron either spikes or it doesn't. Whereas in deep learning system, we tend to transmit really high precision numbers, and that's part of the reason deep learning systems are so expensive and energy inefficient. So if we could get to the point where we can transmit essentially binary information, there's a chance we could make deep learning systems really, really efficient. Um, and so that's one area where the spiking, it may be important to model spiking. But by and large, in our work, we haven't found it really necessary to model kind of the details of all the details of spiking as it is in biology. So again, with neuroscience, it's always a question of where do you draw the line? What level of detail do you incorporate, and what level you don't? And so this is where we're kind of on the border of.
And I imagine that that is a kind of a combination of intuition and experimentation and seeing what works.
Exactly. Yeah, yeah. We try a lot of stuff. Our bias is that if something is really prevalent in the neuroscience, if it's really common and a big feature, it probably has some use. And so we do look at all of this stuff pretty carefully, but we don't incorporate it into our models until we can actually come up with a functional reason for it. Like there's some benefit to be gained. But we do look at a lot of these details pretty closely and talk to neuroscientists constantly about this stuff.
Mm-hmm, mm-hmm. So we've talked about cortical columns, the neuron model, kind of from the biological neuroscience perspective. How do these concepts translate into things that learning machines, for to say it broadly?
From a cortical column perspective, if we can, understanding that architecture helps us, uh, what should help us design better kind of modules and layers in deep learning system. In a deep learning system today, it's very, very simple. You have a convolutional layer or maybe even a transformer linear layer or something like that. They're very simple layers. What the neuroscience tells us is that each layer is a lot more complicated, has a recurrent structure, and it gets sensory input and motor output. So we can actually take the notion of what a layer is in deep learning and incorporate some of these other elements into it and make it a lot more um, complex. And that will provide a lot of benefits. So I mentioned the idea of continual learning, for example, the ability to learn new things without forgetting stuff. But more importantly, if we can make these layers inherently sensory motor, what we can build in are layers that really understand the 3D structure of the world and the physical structure of the world. They inherently understand it. They build 3D models at every level of the hierarchy. And this will allow you to have extremely robust neural networks that don't get fooled very easily with you know uh, input that's slightly different from what it's seen before. It should lead to neural networks that are much more invariant to distortions and things like that. Today's neural networks, you really have to show it, let's say you're doing a visual system, you have to show it images of every object in every possible pose and every possible lighting condition and all of that stuff. Whereas if you can really inherently understand the structure of stuff, the amount of training data you will need will be dramatically smaller, and the representations you build, which will be much more robust and invariant. So these are the kinds of properties I think we can really build in at a very fundamental level into deep learning systems by taking clues from biology.
What does it mean for a model to have an inherent 3D understanding? I mean, it's all
Yeah.
numbers at some point, right? Are we talking about like changing the coordinate system to something polar or?
It's a it's a fantastic question. It's something we've worked on a lot. Exactly that question, and we published this theory called the thousand brains theory. So this idea
Mhm.
that cortical columns, there are thousands of these cortical columns, and each cortical column is kind of this independent modeling system. So what the thousand brains theory says, and this is a lot of it's derived from neuroscience data, is in each cortical column you are building up models that are based on coordinate systems, just like you mentioned. So there's something essentially reference frames in each cortical column, and you can think of cortical columns as building maps of the world. So just like you have a physical map that might show a city and shows how you can move around a city and what's located at different GPS coordinates, along the map. In the same way, when we inherently build up a structured model of an object, we create a 3D map. And in that map, we associate locations with features and properties of the object. And we know how you can manipulate that object, we can make predictions about what will happen if you go from one part of the object to the next. And that map is in what we call in the reference frame of the object itself. It's not in the observer's reference frame. It's in the coordinate system of the object. And so that's essentially what we mean by inherently understanding the object. You would build up this really detailed map-like structure of objects um, in its own reference frame. And we may be viewing it from many different angles and many different ways, but all we have to do is translate that new viewpoint into this map-like structure, and now we can navigate and understand how that object works. So this is so that was quite a mouthful. There's a lot of stuff in there, but inherently we're building up these map-like structures, that contain the full kind of physical and geometric structure of objects and concepts and so on.
Yeah, it's reminding me in some ways to the I'm blanking on the model, but like Jeff Hinton's
Mm-hmm.
the name of the model, but Jeff Hinton has been talking about this post convolutional
Yeah, yeah.
model that has these properties of being kind of more spatial and translation invariant and things like that.
Yeah.
The
So he came up with this idea capsules. Maybe they're thinking of
capsules, right?
capsules. Yeah,
Caps
yeah.
nets.
So Jeff Hinton, has actually been thinking about these ideas since the 70s. We found papers of him writing in the 70s about how we need to build up object-centered
Mm,
representations that are at object-centric reference frames. So he's been thinking about this a long time,
yeah.
and says everything I mentioned is definitely very much in the same kind of line of thinking. I would
Okay.
say what we've learned from the neuroscience is that these cortical columns are much more powerful than we thought. It's much more than what a capsule does. Um, they're really independent modeling systems, and they're inherently sensory motor. So motor actions and predictions are an inherent piece of this puzzle. And so these are all aspects that have to be incorporated in as well. But definitely very, you know, I think there's some truism in deep learning that no matter what idea you think of, Jeff Hinton has probably thought of it 20 years ago. So
Fair
he's
enough.
great.
Fair enough. Kind of a similar question to the last one. What does it mean for these computational models to be inherently sensory motor? Is that implying like a system level connection between, input sensors and representations or something else?
Yeah, so basically, cortical columns send out motor commands, and so there are 150,000 of these cortical columns. They're all sending out signals to your motor systems. So whether it's manipulating your hands, your eyes, or your head, your speech systems, all of that stuff is getting those what we call subcortical structures. Motor systems are getting sort of input from the neocortex, and there's some sort of a reconciliation that has to happen, and again sort of like a voting process, and then the motor system decide, okay, these are the muscles that have to move in this way to achieve the goal that the neocortex is telling me. So basically there's some sort of to use reinforcement learning terms, there's an action policy. There's a lot of possible actions that could happen, and there's some arbiter that's figuring out, okay, what is the best thing I should do at this point in time.
It's still not clear to me how that necessarily what that looks like from a systems perspective, although it does prompt this really interesting thought that kind of echoes RL or even like an active learning where, today collect a bunch of data, throw it at some model and train it, and the model doesn't really have anything to say about the data that it receives. And this is kind of suggesting an active learning esque kind of inherent capability to the model where it is telling some downstream system what it needs to perform. Is that that sounds
Ex-
aspirational as opposed to like what we're doing today?
Yeah, yeah. I mean, it is. It's exactly that. It's an active system, and it's what brains are doing constantly.
Yeah,
You and I are
yeah,
doing this right now, and so we are not passive systems, and
right.
so we are inherently active, and that is a large part of why we are so able to learn. Fundamentally what how our world works.
Mm-hmm.
Um, and so, it's a predictive system. So when we send out motor commands and send out actions, we make predictions about what we're going to see. And based on what we actually end up sensing, we can update our internal models um, using the error in the predictions. And this is an extremely efficient way of learning. Um, and so and we're going to take actions that are going to tell us most about the world. If I've seen something over and over and over again, I'm mostly going to ignore it. I'm going to go for the novel stuff, and that's how I'm going to learn most quickly. So it's as opposed to seeing the same data over and over again, you'll really become efficient at how you learn stuff.
Yeah, yeah. I think part of the way I asked the last question was trying to get at like where are we today with this line of research? Granted that it's research and it's trying to do big things that are modeled on biology. But what indications do you have that it is a promising direction to go to build the kind of systems that we want to build, whether that's what today's deep learning is doing or what we want it to do in 10 years?
Yeah, it's definitely still research. I think we're making really good progress on it. We are focused on building sort of initial machine learning based models of these cortical columns, trying to figure out exactly how these reference frame transformations should happen. How do you build up these object centric models? And then, some of the issues we discussed about how do you, take the motor signal or the action output and then translate it into movements of your sensor and so on. So we're making really good progress on that, but we definitely don't have the full system working yet.
Yeah.
But I don't want to put timelines on it, but it's something we're really excited about, and hopefully we'll have stuff to announce on that soon. Yeah.
Nice. You mentioned sparsity as kind of this foundational property of
Yeah.
the way that you build out these models. Can you elaborate on that a bit?
Yeah, yeah, I can talk quite a bit about that. In contrast to the cortical column stuff, which is there's still quite a bit to figure out, and we're making good progress on it. I would say the sparsity stuff is something that's really practical, and we've shown a lot of use cases today on large scale models and small scale models in deep learning. So sparsity is basically when you have weights that are weight matrices or weights that are mostly zero, meaning that there's a very sparse set of connections between layers. In the brain, you see another type of sparsity, something we call activation sparsity, meaning very few neurons are firing at a time. Um, so, only about 1% of neurons in your neocortex are firing at a time, and so there's sort of connectivity, sparsity in connections, and sparsity in activations. And both of those factors can actually lead to tremendous efficiencies in processing deep learning systems. The brain uses only about 20 or 30 watts of power, which is pretty amazing when you consider the billions, tens of billions of neurons in there. And you can compare that with today's GPU based systems, which are power. You could probably power a small village with with some of the clusters that are out there. Um, and the way that this works is basically, if you have zeros in your weight matrix, you can skip that multiplication because you know already that multiplication is going to be zero. There's no point doing that multiplication. And if you have both activations that are sparse and weights that are sparse, you get this multiplicative effect where a fractional percentage of the multiplications actually have to be performed. So one way to think about this is, suppose you have 90% weight sparsity, so only 10% of the weights are non-zero. So you could imagine like a 10x gain. You can skip 9/10 of the multiplications. But if you also have 90% activation sparsity, only 1% of the products are going to have non-zeros on both sides. So you can skip 100 times the computation. There's this sort of multiplicative effect that happens. And what we've focused a lot on is, how do you translate that into deep learning systems that are accurate? At the same time, how can you translate that into hardware architectures and actual implementations that can actually exploit that efficiency? And those are both areas that we've started to make tremendous progress on, and learn quite a bit about.
And how do you go about approaching that? It strikes me as kind of the classical 10 cent for the nut and $1,000 for knowing where to put it, right?
Yeah, exactly. Yeah, I mean, that's actually a great way to say it, because what we've been doing in deep learning is throwing more and more compute at the problem, right?
Uh-huh.
And it's great for some companies that are making GPUs. It's fantastic for them. They just want to throw more compute at it. But it would be even better if you just didn't have to do the compute, right?
Yeah.
At all. That's what sparsity allows you to do, is sort of
Right.
knowing where to skip the compute. and
Right.
and so there are two challenging aspects of that. One is, like, how do you even train networks that are accurate and but have all of these zeros flying around all over the place? Um, and the second piece is, how do you actually translate into hardware architectures? And so, with the first part, in training, what we have found is that there are a bunch of different ways you can go about it. One sort of critical aspect is that the way you train sparse networks is different from the way you train dense networks. And in particular, with deep learning, you have to really be careful about your parameters and how you set up the network and how you set up the experiments, and really explore the hyperparameters and so on. And with sparse networks, what we found is that you need to do your own hyperparameter exploration in a way that's quite different from the way you do dense networks. And so uh, that's one of the big things that we've learned coming out of this.
What is it about sparsity versus denseness that drives this different way that you need to approach it?
So, a lot of deep learning systems are trained using backpropagation, and backpropagation inherently assumes you're in this dense n-dimensional space, and it's trying to move around this n-dimensional space. Whereas if you have a sparse system, an exponentially large percentage of that space is just out of bounds, and so you just can't go there. And so you're really fighting against what backpropagation wants to do. And so we've had to use a lot of tricks and hyperparameter optimization techniques. We use a technology from a company called SIGOPT that has this sort of Bayesian hyperparameter optimization techniques that's worked really, really well for us. And we've used that to figure out exactly what combinations of hyperparameters really allow backpropagation based networks to effectively kind of navigate that space, and find global optima, or something close to global optima.
Have you kind of measured or how do you measure even the difference between trying kind of standard backprop versus more of an optimization type of an approach?
Yeah, so backprop, it's you're typically computing some sort of a loss function or an error function, and you kind of measure that. What's important for us is not just that error function, but also other things like sparsity, like activation sparsity and stuff. So we have to measure multiple things at once. So it becomes a more complicated optimization process. It's not as simple as just finding the lowest error. You need to find the lowest error in conjunction with networks that are as sparse as possible from a connection standpoint, and as sparse as possible from an activation standpoint. And so doing this sort of multi-metric optimization is quite tricky. And this is where sort of the SIGOP technology that I mentioned really helped us, and really shines in that respect. So yeah, it is tricky to figure out, yeah, how do you measure it and how do you go about doing it. There was a lot of learning that was involved in that.
And is the this optimization process, telling you is it telling you broadly, like is it giving you some broad parameter around sparsity, like level of sparsity, or is it telling you specifically, at any given time step in a training loop, like what neurons don't need to worry about?
Yeah, it can tell us both actually. So yeah, and so in some cases we know what level of sparsity we might want in the weights, but we have a lot of freedom in how much activation sparsity can have as one example. And so you want to be able to balance accuracy versus sparsity in that case, and it can help guide in both areas.
I think what I'm trying to reconcile is if you're if each of the weights, or if each of the weights is a metric that you're trying to
Yeah,
optimize, the spaces, the dimensionality of the space is ridiculous,
right, right.
right? That is that what you're doing?
Yeah, it's something we call it's not so it's something we're doing, it's also something
Okay.
the brain is doing. So
Okay.
what people may not realize is that the connectivity in our brain is actually not fixed. The neurons in our brain are constantly adding and dropping connections, so it's something we call dynamic sparsity. That the connectivity itself is being learned, which is kind of mind-boggling to think about. Um, Something like I saw a study that in the adult brain, something like 30% of the connections are different every few days,
Wow.
which is just a staggering number to
That's
think about.
nuts.
That
Yeah.
it says your brain is going to be quite different a few days from now. And what's going on is that neurons are constantly trying to learn new things and forget about the stuff that's no longer relevant. So you have your core memories that are going to be stable, and then you're constantly trying to learn new things. And this gets back to the continual learning thing I alluded to earlier. We're constantly trying to learn new things, and the brain does that by growing new connections really quickly. And then if something sticks, those connections will become stronger. But most of the stuff we see day to day are just random connections and spurious connections. So those will drop off. So that's kind of what's going on. Now we have to translate that to deep learning, where you have to actually learn the mask over the weights, if you will, like which weights are going to be on or off. And yeah, that makes the whole process quite interesting.
And I'm still like, is the are you learning the mask at the individual weight level, or is that parameterized in some way? There are, some smaller dimensionality of like mass patterns that you're optimizing over.
Yeah, it's a great question, actually. We just published a paper called Two Sparsities Are Better Than One, where we showed that when you think about hardware architectures, you actually have to be careful about the sparsity patterns, because some sparsity patterns will map really well to the hardware and others won't. And so we've come up with some techniques called complementary sparsity, where there's a set of patterns that map really, really efficiently to the hardware. And so you want your training algorithms to understand the constraints of the hardware in this optimization process. And if you can do all of that stuff well and balance everything well and still get really accurate networks, we've shown you can get actually 2 orders of magnitude improvement in performance. So you can get networks that are 100 times faster on the same hardware, um, uh, than a corresponding dense network would be on that architecture.
By hardware here, we're talking about GPUs or FPGAs or.
Exactly. Yeah. So the paper we published was a proof of concept on FPGAs. And the nice
Okay.
thing about FPGAs is we can really design the circuits to be exactly what we want.
Hmm.
We actually think you can take those same ideas and apply them to CPUs and GPUs as well. There's some additional tricks that are involved, but we're making good progress on that. So we think, sort of stepping back a little bit, we think if you can be really smart about where you place the zeros and what computations to avoid, we think there's a potential of making deep learning orders of magnitude more power efficient and more compute efficient than it is today. And if you think about kind of the carbon impact of deep learning today, which is just insane, it sort of behooves us as an industry to really pay attention to this and really improve the energy usage of our deep learning systems. It's kind of completely out of control today.
And you're saying deep learning, and just to be absolutely clear, you're talking about conventional deep learning, for lack of a better term, as opposed to what we were talking about earlier, cortical columns, different neuron models, things that where you're working on in the research. This is applying sparsity and optimization to drive greater efficiency and something that's roughly akin to what we're doing today. Is that fair?
Yes, yes. The sparsity stuff could be applicable in today's deep learning networks. It seems it's becoming more and more clear that these sparse techniques can be applied to basically all of the network architectures that are out there today, whether it's convolutional systems, transformers, conformers, ResNet, all the different architectures that are common today can benefit from sparsity. Having said that, the cortical column implementations when we get there will also be sparse, because the brain is sparse, and sparsity gives you tremendous benefits. But the good thing about the sparsity work is it can be actually applied today to today's deep learning systems.
And is sparsity, is it an emergent property of the architecture, or is it the use case or the data? Is it something that you can always apply and it has some benefit because it's broad, or is it only if your data or your problem looks a certain way?
You can apply it to almost any problem domain. Where the thing you do need is that you need networks that are larger. It's sort of a little bit paradoxical think about, but you need larger networks in order to allow really sparse processing. And what happens mathematically is as you get larger networks, you get these exponentially larger spaces that you're working with, and it's easier and easier to find solutions that can be extremely sparse in there. So even if you look at the total number of non-zero weights, if you have a small network, maybe you can get to, let's say, uh, 1,000 non-zero weights in a layer, just to pick a number. If you have a larger network, you might actually be able to get to 500 or 100 non-zero weights. So it's counterintuitive, but by making the dimensionalities bigger, you can actually get by with smaller absolute number of weights. Yeah.
Is that a property of Bayesian optimization in particular, or something else that the
This is
larger
just a
the space?
Yeah, this is just in the mathematics of sparsity. The
Okay.
way it works is that as the spaces get larger, you can get the same amount of information with a smaller number of weights. So it's an
Mm-hmm.
information theoretic result. There now, obviously from a Bayesian parameter optimization standpoint, it just makes it even harder to find all these hyperparameters and create
That
networks that can
yeah.
train and that. So
You mentioned in the application of the Bayesian optimization stuff that you were doing. We talked about the multi-metric nature
hmm
of it. Uh, you also said some things that sounded like kind of constrained optimization, which I know SIGOP does as well. Is that something that you're using as
yeah,
part of the formulation?
yeah. So with the multi-metric, we can optimize multiple quantities simultaneously, like sparsity and error and so on. With constraints, we are using constraints. So with SIGOPT, you can put all of these constraints in your parameters. So we make sure that we stay within ranges that we know will work well. Um, uh, you know, uh, so for example, constraints that we know are imposed by the hardware. Um, uh, or there's combinations of hyperparameters that just don't make sense. And so those we want to put those constraints so that the hyperparameter optimization doesn't visit parts of the hyperparameter space. That's a mouthful. that it does that just don't make sense. Um, yeah, I mean, with hyperparameter optimization, every point in the space is an entire training run, and so you have to be judicious in how picking those points efficiently. And so the constraints, any constraints you can put in that will just reduce the space of possibilities and make the entire process a lot more efficient.
You mentioned transformers a couple of times. Have you applied any of the sparsity techniques that we're talking about to transformers and language models, and some of the things that are potentially causing, the large environmental impact that you alluded to?
Yeah, yeah, it's exactly because of that that we are actually spending quite a bit of time on transformers. They're becoming very popular, um, but at the same time, these are just massive models that are taking up, consuming huge amounts of power, and creating a pretty big negative environmental impact today. We've having quite a bit of success in sparsifying transformers because these models are larger. It's possible to get quite sparse with that. So we've been able to get transformer models. We've worked with the BERT model, which is kind of the canonical transformer model that everyone uses as a kind of a template. We've been able to get to 90% sparse and even higher without losing accuracy. Um, in these kind of models. So there's a potential of really accelerating these transformer models and making them much, much more power efficient. So we published a blog post on that recently, and we should be um, having a lot more on that in the coming few months.
We'll definitely include a link to that in the show notes pages. Is there a rule of thumb that 90% sparse translates to, 50%, power or something like that?
We think with the right hardware optimizations, 90% sparse should give you more than a 10x gain. So we're not talking about 50%, 20%, 30%. We're talking about orders of magnitude here. Um, and so with 90%, you can skip 9 out of 10 computations, but your model also gets really smaller. So you get additional advantages over that. So if you in hardware, you have memory hierarchy. So some memories are faster than others, and a smaller model means most of your model can fit in these faster memory areas, and memory contention gets much smaller. So there's a bunch of other practical things that come in. So we eventually think we can get more than a 10x with that. The brain is 95 to 98% sparse. So if we can get anywhere close to the levels of the brain, we're talking, and again, remember there's multiple types of sparsities that interact and have multiplicative benefits. So we're talking multiple orders of magnitude efficiency gains if we can really get close to how it is in the brain. Um, and I think a lot of deep learning researchers used to think that was impossible, but I think the brain shows that it's not only is it possible, it's actually the best example we have today.
Right. Uh, I'm curious about, we've been talking about training slash learning. What about the inference side of things uh, with regard to sparsity?
Yeah, so but both inference and training will speed up with
Mhm.
sparsity. We focused actually a little more on the inference side because that's the more kind of common use case, but training will speed up too. But the fundamental mathematical operations that occur during inference and training, they're very similar, and so they should both benefit from this.
Awesome. Awesome. Well, we've covered a ton of ground. What are you most excited about over, say the next 10 months or some other arbitrary time horizon?
Yeah, what's there's this big question in the machine learning community, like, can brain inspired understandings actually impact machine learning
Okay.
positively? And I think I'm really excited that the stuff that we mentioned is now coming into real practical domain. And with sparsity, I think 10 months from now or a year from now, we'll see really dramatic improvements in what we can do from an efficiency standpoint. And I'm really hopeful in that time frame that we'll be able to take many more of the ideas of the cortical column and start showing really concrete, hardcore benefits to machine learning systems, and to really showcase that we can take, understanding the brain is not just an academic scientific exercise. It can actually have practical engineering benefits, and to me, that's what I'm really passionate about as a computer scientist. And hopefully, a year from now, we'll be in a dramatically better space with respect to all that than we are now.
Fantastic. Fantastic. Well, Subutai, thanks so much for taking the time to share a bit about what you're working on. It's very cool stuff.
Yeah, thank you so much, Sam. It was a pleasure talking, and those were great questions, and I'm glad we got it time to go into a lot of the detail on that.
Absolutely. Thank you.